Hello everyone, and welcome to another episode of Power Logic. So today we're going to be going over problem 8 on the 2022 Aime Ii. Find the number of positive integers n is less than or equal to 600 whose value can be uniquely determined when the values of the floor value of n over 4, the floor value of n over 5, and the floor value of n over 6 are given, where the floor value of x denotes the greatest integer less than or equal to the real number x. So for example, the floor value of 1.5 is just equal to 1, since we're basically rounding it down. Now, how are we going to start with this problem? Well, often I would say a really good technique to start off problems would be try to find some patterns. So in this case, we would be more helpful if we can actually list the set of values of these three floor values for each of n to see what kind of n would actually satisfy the uniquely determined condition. Now let's just make a table. Which I would say that this is x. Then we're going to have, let's just call it like f of x. Now we're just going to start. So first we're going to try 1. So 1, what is the floor value of 1 divided by 4? Well, it's just equal to 0. And so does 5, so does 6. And notice that for all of the numbers that are less than 4, this floor value would always be 0. So 2, we also have three zeros. 3, we also have 3 zeros. Now what about 4? 4, we're actually going to have some change. 4, we're going to have one more. 4, we're going to have one more when n divided by 4. The floor value when 4 is divided by 4 is equal to 1. And for any others, it still does not change. However, for 5, we also have another change. So you can see that we're actually going to have one more for each of multiples of 4, 5, and 6. So let's continue to try some numbers. So 6, we're going to have 1, 1, and 1. And what about 7? Let me extend this. For 7, we're not going to have any change. For 7, we're just going to have 1, 1, and 1. For 8, since 8 is a multiple of 4, then we're going to have one more and the floor value of 4. And then we're going to have 2, 1, and 1. And 9, still, 9 is not a multiple of 4, 5, or 6, so therefore there are no changes. Okay, now we just finished listing all of the numbers from 1 to 16. Now, the red numbers denotes those numbers that have changes with the three numbers. Either one of the three numbers or two of the three numbers. Or all three, but it's not possible right here. So, now, let's try to find a pattern about what is so special with these numbers. So, we have 4, 5, 6, 8, 10, 12, and 15 and 16. And look at the three numbers that what we were doing. 4, 5, and 6. Well, can you probably try to find some pattern? Or, in other words, is there any relationship between these numbers and these three numbers? Yeah, these numbers must have to be one of the multiple, right? At least one of the multiple. You must be either 0 mod 4, 0 mod 5, or 0 mod 6. For example, 4 is a multiple of 4, 5 is a multiple of 5, 6 is a multiple of 6, 8 is a multiple of 4, 10 is a multiple of 5, 12 is a multiple of both 4 and 6, 15 is a multiple of 5, and 16 is a multiple of 4. So now, however, keep in mind that we want to find the numbers who can be uniquely determined by the three values. So basically it means that there's exactly one such numbers whose three values has this representation. For example, for 5. For 5, only 5 have this combination of the three floor values. Since we're changing in 6, and we're changing in 4. And we're also changing in 5. So therefore, there's exactly 5. There's exactly one number that have this kind of representation. So now let's try to see what numbers satisfy such condition. 5, 4, 15. In the first 16 listed. Now can we actually also try to find something special about these numbers? Yeah, these numbers are one less than another multiple of a different number that belongs to one of the three numbers. For example, for 4, 4 is a multiple of 4, but one less than a multiple of 5. 5 is 0 mod 5, which is a multiple of 5, but it's one less than the multiple of 6. And so it's 15. 15 is a multiple of 5, but it's one less than a multiple of 4. But when you look at 6, 8, 10, and 12, they do not satisfy this condition. Well, why is that? Because you have another number that satisfies this combination. So therefore, these are not unique. So now let's probably draw some conclusion, which is either an algebraic statement or just some like pseudocode style thing. So now, what is the pattern? So if A is a number that we want to find that satisfies that it can be uniquely determined if it's given the three values, then A must satisfy 0 mod P 1, and A must satisfy -1 mod P2, which let S be equal to this set, which P1, P2 belongs to this set. And obviously P1 cannot be equal to P2. Well, now I believe that there's probably some better way to do it, but my own way would be just to list all the multiples of 4 multiples of 5, and multiple of 6. And now, we do not want to try all 600 numbers. So we can just try from 1 to 60, because once we reach 60, then all modulos, since 60 is the least common multiple of 4, 5, and 6. So therefore, the module just resets. So therefore, we just check from 1 to 60. So what are the multiples of 4 between 1 and 60? 4, we have 1, we have 1, 2, no. $20, $24, $28, $32. Excuse me, but let me expand this to $36, $40, $44, $48, $52, $56, and we also have $60. Now what about multiple of 5? Multiples of 5. Just expand it. We have 5, 10, 15, 20, 25, 30, 35. Or technically, we just want the odd. We just want the odd multiples of 5. Well, why is that? This is because if we have 0 mod 5, then if it is an even multiple of 5, then it's impossible to be equal to -1 mod 4 or -1 mod 6, since both of these will result to be odd numbers. And if it's -1 mod 5, then it's odd, so it's impossible to be divisible by 4 or 6. So we just want to list out the multiples, the odd multiples of 5. And 6. Okay, so we're done listing. Now we just want to find any pair of consecutive numbers within all of these. So first, let's start. We can see that there's actually 1, 4, and 5, 5 and 6, and 15 and 16. Wait, let me just write it down. So we're going to have So we're going to have 4 and 5. 5 and 6. Then we have 15 and 16. Now what else? 24, 25. And then we're going to have 35 and 36. And 44 and 45. And we also have 54 and 55. Also have 55, 56. And that is essentially it. So you have 8 in the first 60. Now if you guys remember that I said that everything resets after 60, then basically we just want to find how many intervals between 1 and 600 are there. So obviously there are 600 over 60 is equal to 10. It's obviously 600 over 60 equal to 10 such intervals. And we just want to multiply 8 by 10. And this will just give us 80 as our final answer. Well, the insight of this problem, I believe that there are actually multiple ways that will be more convenient. For example, the Chinese remainder theorem. However, I will say that often when you're doing problems, if you're stuck with trying to find an elegant solution, then bashing or brute forcing are not always a bad idea to try out. And often like this, bashing or brute forcing might actually be faster. So therefore, don't always get stuck into one of the methods, but always try to think of the new method and think outside the box. And when you cannot do that, then don't forget to just try to brute forcing, since these can often give you the result and the correct answers. Or at least you should try to find some patterns. For example, in this problem, well, it will actually be really challenging to come up with this kind of insight or this kind of pattern without trying to list the numbers.